Good afternoon to all of you. I guess we'll start. Please confirm that you are able to see the slide.
Yes, sir.
Thank you. We'll just advance the discussion that we have been doing a bit further today. We are looking at the method of small disturbance analysis, which eventually leads to a non-dimensional similarity-based approach with specific emphasis on hypersonic applications. The benefits of it are obvious because of the easiness with which some of the parameters like surface pressure distributions can be estimated. And we have seen the most fundamental aspects of it. That is, we consider the velocity field to be perturbed, that is disturbed a little bit by the presence of the body. The disturbance is small in relation to the mainstream velocity. And because of that, we can neglect some of the terms that would eventually manifest in the relation. And based on that, we can restate the governing equations by adding the velocity components u dash and v dash to the x and y components of the velocity. And we can restate the equations, and by appropriate non-dimensionalization of the parameters, we can change the terms in such a way that they will be of either magnitude 1 or they will be of the magnitude of tau squared. Now, tau is d by n, is a measure of the bluntness, which is the inverse of slenderness. So tau is less than 1 by assumption because we are restricting our attention to slender bodies, and we have seen the justification for it in everything. Hypersonic everything propulsion, most of the attention is on slender shapes, so it still has some validity. So when tau is less than 1, tau squared is much lesser than 1, which means that if there is a way by which the equations can be rewritten in terms of relation, in terms of parameters which are of the order of magnitude of 1 and order of magnitude of tau squared, then the terms that include or the terms that are of order of magnitude tau squared can be neglected because tau squared is much less than 1. So that's the approach actually. So it's a admittedly it's a very artificial way of transforming the equations in such a way that we have the terms consistent with the requirements that we have in mind. But then physically it is okay because we are though we are sacrificing some accuracy, we get useful initial results which are the objective of such an analysis. I guess we have discussed these terms yesterday. The orders of magnitudes of different ratios like rho 2 by rho infinity is around 6, we know, for gamma equals 1.4. That's order of magnitude 1. Similarly, rho dash is rho by rho infinity, u dash u2 by u infinity tends to 1 minus 2 into sine squared beta by gamma plus 1 for high values of Mach number. And eventually we have seen that u prime dash, or rather, u prime dash, the non-dimensionalized velocity perturbation can be described as u dash by v infinity into tau squared. V infinity is a high value, but tau squared is a very low value. U dash is a very low value. So in as a result of it, this fraction u dash by v infinity tau squared will turn out to be of order of magnitude 1. So some of the terms, so by proceeding like this, some of the terms become order of magnitude 1 and some of them becomes order of magnitude tau squared. Tau squared is negligible as compared to 1 because we are considering slender bodies. Now other we have fractions like delta v by v, that delta v, that is the velocity component in the v direction, in the y direction, which is actually v2 because to begin with the free stream velocity does not have a y component. So delta v itself is v2. So v2 by v infinity and that comes out to be sine 2 beta by gamma plus 1, given the original relation here, which is what we have from the oblique shock relations, that is V2 by V1. Remember, V2, the small V2, is the component along the y-axis. Okay, and V1 is the mainstream velocity. So V2 by V1 can be expressed in terms of the mainstream Mach number m1 and the shock angle beta. So that's what boils down to sine 2 beta by gamma plus 1 when m1 squared tends to infinity. Okay, so this term sine 2 beta by gamma plus 1 can be of order of magnitude tau. Tau is a small parameter, sine 2 beta. Beta is small, sine 2 beta is also going to be small. Gamma plus 1 is going to be that is going to be 2.4. So this ratio sine 2 beta 2 beta divided by gamma plus 1 can be assumed to be of order of magnitude tau. Now, with that, we have pretty much all the parameters which are non-dimensionalized, like x bar is x by L, y bar is y by L tau. Tau is L by D, right? Tau is the inverse of L by D, that is D by L. Then Z is also non-dimensionalized in a similar way. U bar, U dash bar, we have seen that already. P we have discussed already. P bar is P by gamma m infinity square tau square P infinity. Please look at that. P divided by static pressure divided by m squared, m infinity squared tau squared. M infinity squared tau squared. That is, m infinity is a high value, tau is a small value. So m infinity squared tau squared, that's the importance of the product there. P by P infinity, and then gamma in the denominator as well. And then rho bar is equal to rho by rho infinity. Now, the way that all these forms, equations that we have, or sorry, the fractions that we have, or rather non-dimensional parameters that we have, they are all of order of magnitude 1. I guess I had shown P bar in one of the earlier slides. Yeah, sorry. I don't know whether I missed out explaining this, but then at least that P2 by P infinity I'll show from here. P2 by P infinity. P2 is the pressure after the shock, static pressure. P infinity is the static pressure of the undisturbed free stream approaching flow. For when m tends to infinity, etc., the value of this tends to 2 gamma by gamma plus 1 m infinity squared sine squared beta. Now, P2 by P infinity, where you have m infinity squared sine squared beta here, and what multiplies it is 2 gamma by gamma plus 1. 2 gamma is, say, gamma is 1.4. This is 2.8 divided by 2.4, etc. So that value is going to be of the order of magnitude of 1, and then m squared sine squared beta. The sine squared beta we have seen here already is of the order is equal to sine theta. Why? Because we are considering slender bodies at high Mach numbers. This we have seen much earlier. That is when in hypersonic flow, the difference between theta and beta is very small. So sine beta approaches sine theta for small values of beta and m infinity. And since the value is small in terms of radians, etc., it can be equal to theta. Theta is actually dy approximately equal to dy by dx, which is basically tau. Tau is the d by L, the bluntness ratio or the inverse of slenderness ratio. So this relation, what we have here for P2 by P infinity, that turns out to be of the order of magnitude of m squared, m infinity squared, tau squared. Because sine beta is almost equal to tau, so sine squared beta is equal to tau squared. So m infinity squared, tau squared, and the product what multiplies it is 2 gamma by gamma plus 1, which is anyway of the order of, can be considered to be of the order of magnitude of 1. So two products of two terms which are of order of magnitude 1 is again of order of magnitude 1. So 2 gamma by gamma 1 plus 1 can be considered to be close to 1. So m squared sin squared beta can be considered to be order of magnitude of m squared tau squared, because sin squared beta is approximately equal to tau squared. Okay, so what we carry forward from here is that m p2 by p infinity is of order of magnitude of tau squared. So because of this, when p is normalized in this way, p bar by that is equal, p bar is equal to p by gamma infinity m infinity squared tau squared p infinity multiply, sorry, gamma, the denominator is gamma infinity m infinity squared tau squared p infinity. This is the way p bar is normalized, is non-dimensionalized. Now that's a term that we have here, where it is the because of that particular or because the way that we have non-dimensionalized it ensures that p bar is of order of magnitude 1, because as we have just seen, p by p infinity is there and m squared tau squared is there in the denominator. P by p infinity is already or of the order of magnitude of m infinity squared tau squared. So the ratio of them is going to be of the order of magnitude 1. Okay, so that's so actually it's an artificial way of rearranging the terms in a way that they have the required order of magnitude that we need for simplifying the equation. So by this process of simplifying and non-dimensionalizing, the hypersonic perturbation equations can be written as, I'm just saying can be, that derivation is a long mathematical process, let's leave it aside. With that, with the terms that we have defined, I reproduce them again here on the right hand side. All the parameters, that is x bar, y bar, z bar, u prime dash, v prime dash, and w prime dash, and p bar, rho bar, etc. All of them are replacing the original variables in, and this, if you do though so, and by eliminating terms which can be neglected, I repeat that, eliminating terms which can be neglected in comparison with order of magnitude 1, then we can rewrite the equations purely in terms of the perturbation variables as shown here. So how we arrived at this is by redefining the parameters and redefining them in such a way that they many of them will turn out to be of order of magnitude 1, and many of the other terms will be order of magnitude tau squared, and order of magnitude tau squared can be neglected in terms of in comparison to terms which are of order of magnitude 1, because tau squared is much less than 1. With that approach, we have the hypersonic perturbation equations written in this manner. And they're still, I mean, yeah, it's not that we have got a lot of simplification in terms of the nature of the equations. They still continue to be partial differential equations, non-linear partial differential equations. So the nature of the equations is not simplified much, but we have certain benefits in terms of the terms that we have there. That's what we are going to see next. So as I just mentioned, we have a set of coupled non-linear partial differential equations. So obviously they are non-linear partial differential equations, so there is no analytical solution. So we cannot hope with all this simplification, we are not still hoping for an analytical solution. They cannot have an analytical solution. And because the inherent non-linear nature of hypersonic flow prevents or makes it impossible to have any analytical solution. Now, this set of equations can be made use of to do what we call as the hypersonic similarity analysis. So that's the culmination of the reframing of the governing equations in this fashion. The end product of that is going to be what we call as the hypersonic similarity analysis. Now, before we examine that, please be reminded about similarity analysis. If you have bodies which are geometrically similar, you have studied about geometrical similarity, dimensional similarity, etc. in fluid mechanics when you studied the non-dimensional analysis. So, for example, two bodies, say hypothetical hypersonic type bodies, which are shown in this one. Say they are geometrically similar, but they are not identical, right? That's where you use similarity approach, right? You have two physical situations which are similar in certain aspects, but they are not exactly similar. If they are exactly similar, then you don't have to have, you don't need any correlation, because whatever happens in case one will happen in case two. If they are similar, same conditions and same geometry, then the results are also going to be the same. So you don't require any analysis for that. The importance of similarity analysis is when you have two physical situations which are similar in several aspects, but basically in different, intrinsically, or rather, which have certainly two different certain aspects which are highly different. In such cases, when you strike an equivalence between the behavior of the flow from one case to another, that's what we mean by similarity analysis, which is extensively used in fluid mechanics, heat transfer, aerodynamics, etc. Now, how do we how do we generalize the approach? It's basically I'm just going box by box. The first one, the whole approach is to express equivalence between two physical situations, two physical phenomena or two physical occurrences, which are similar in certain way, but not identical, because there are some dissimilarity. I just remind you, they are similar, but say for example in this case, the configurations are similar in certain aspects, but then as we can see, the slenderness is different. T1 is higher than T2, the thickness or whatever the transverse dimension is higher for one case. Okay, so they have some differences, but overall they look to be some of the important parameters are similar. Now, in such cases, we can strike an equivalence between the phenomena of the two, and that is what we call as the similarity approach. The complex physical phenomena can be expressed in functional form, say like as you talk about Reynolds number, OVD by mu, Mach number. All those are, in a sense, they are functional relations which are expressed as non-dimensional parameters. So when we say Reynolds number for two different spheres of two different diameters, they are different because diameters are different, but they are similar because they have their shape is similar. In addition to that, if they have same Reynolds number also, then non-dimensional parameters like CD may be same for both. That's basically the approach in non-dimensional analysis. That's what we extend here in similarity approach also. So, and then similarity approach basically reduces the number of parameters that describe the phenomena. Instead of having too many number of parameters to deal with, we can reduce them to a handy number of set, a smaller number of parameters. And that's what we do in similarity approach. And that's what we are doing in hypersonic flow similarity also. So with these equations that we have, what we are now trying to do is to impose boundary conditions in similar way, and then examine what is going to be the behavior of the equations. So again, we are not going to solve the equations, but when we have consistent set of boundary conditions and equations, both expressed in terms of similarity or perturbed non-dimensional perturbation parameters, we can infer certain things about the nature of the results that they are going to give for parameters like surface pressure distribution. And that's what we are going to take from this analysis. Any questions so far? I know that it's a lot of set of dry equations, and often I'm repeating the same concept of similarity again and again, etc. So, but then the whole purpose, I hope, I am actually, hopefully in the next class, I'll be able to show some results and probably some applications of this, which hopefully, so once that is done, and when you revisit the PowerPoints, the slides, hopefully you should be able to relate better to the process. So I know that the intermediate sessions could be sort of so dry, but I hope that when we have some results to put, and unfortunately, unless I go through this, I cannot. It doesn't make sense to put the results up front. So once we see the results, and then if you revisit the slides, I hope it will make better sense. And if you still have doubts, we can discuss them again also. As of now, do you have any questions on this one, etc.? Any points that I need to discuss further? No. So we'll continue this tomorrow for two reasons. I don't want to go through these equations again and again for a longer period. I'm sure you'll be disengaged totally if I continue. One second is I need to right now jump to another meeting also. So for these two reasons, today I'm stopping the lecture today. Right now we'll continue it tomorrow. We'll hopefully complete it tomorrow. Okay.
Okay.
Thank you. Thanks to all of you. Bye.
Thanks.
Thank you, sir.